Dynamic models of sensing element. Actually, it may be very interesting topic for those who are doing research in this sensor technology. But for us, it's not so much interesting. So we will see in brief about this. Means what do you mean by the dynamic models of sensing element? Uh, if we look at example of a computer, laptop, can you represent laptop by a block diagram? So in simplest way, we can represent it in form of block diagram. Input, then processing unit, then display means output. Teeny part, correct? Now the input, it may have number of elements. It is, although it is a block diagram, but actually it has number of inputs. A is connected when I press A, it generates some pulse. Okay, so and so on. Different type of elements may be connected. So can we represent the whole laptop or desktop in terms of a block diagram? So if it is, yes, it can be represented, then we can also model this using some mathematical expressions. Okay, and this modeling, okay, so after modeling, what we will do, we will test it for different inputs. So the common input may be time, means how does it behave with time? Whether the laptop is giving correct display at 6 a.m. morning and 10 p.m. or not. Other inputs may be there, but time. Then other things may be frequency, means if frequency changes, what happens? If particular type of oscillating input is applied, not just DC, A, if we press A, it generates a pulse. Suppose it is generating pulsating input, then how it respond? So in this way, we have to model it. So the dynamics of that, if we are aware about, then we can easily model, we can easily design, we can easily produce it. So that's why it is very important. But for us, we will not go deeper and deeper inside this. We will just see in brief what does it mean. So, so to determine a sensor's dynamic response, a variable stimulus means input should be applied to its input while observing the output values. If we apply the variable input, then see how output it is giving us. Generally, a test stimulus may have any form which should be selected depending on practical need. For example, while determining a natural frequency of an accelerometer, sinusoidal variations of different frequencies are applied. This is just one example. Okay. On the other hand, for a thermistor probe, means by which we want to measure the change in temperature, a step function temperature would be preferable. Step function means at present temperature is 10. All of a sudden it rises to 15. So then and there it must be 15. So step means just at particular time it rises from 10 to from A to B, from one value to another value. So that will be a preferred for the thermistor probe. In other cases, step or square pulse input is often implied. And why it is so? So generally, if we talk about the test signals, so there are basically three types of test signals. One is impulse, second is step, and third is ramp. I hope all you are familiar with these impulse function, step function, and ramp function. So why these are of interest, the interesting stimulus? Reason is that if we look the frequency spectrum of a step function, if we look at the frequency spectrum of impulse, what we will find, theoretically infinite frequency spectrum may exist in these functions. So when this type of input is applied, means we can test the system for infinite frequency spectrum. So that's why these stimulus are very important to observe the dynamic behavior of a sensor system or sensor element. Correct? So first thing is input. Then second thing, the block to which the input is applied. So if we know the dynamic model, if we know the representation of that sensor in terms of some mathematical equation, we can easily obtain the output. So mathematical modeling of a sensor is a powerful tool in assessing its performance. The modeling may address two issues, the static, dynamic. The model usually deal with the sensor's transfer function. Transfer function means if we apply some input, we get some output. Between input output, there is some block that is representing a sensor. Okay. So input gets transferred into output. So what should be the model present in between input and output? That will be referred as the transfer function. Means because it is transferring the input from one type to another type. Okay. So here we briefly outline how sensors can be evaluated dynamically. The dynamic models may have several independent variables. However, one of them must be time, maybe frequency, maybe distance, maybe some other things. But the time is the most preferable, most important variable. The mathematical models are formed by applying physical laws to some simple lump parameter sensor element. In other words, for the analysis, a sensor is divided into simple elements and each element is considered separately. However, once the equations describing elements have been formulated, individual elements can be recombined to yield the mathematical model of original sensor. A simple example. The example is, let's say, piezoelectric crystal. So I do hope everyone is now familiar with the piezoelectric crystal. A crystal, if some force is applied on the opposite faces because of deformation in its shape, on the other opposite faces, some EMF is induced. Okay. Now, if we want to represent that piezoelectric crystal in terms of some mathematical model, so what we can do, we can look the system entirely, then we may see a number of elements are in, number of subsystems are involved in this. And by taking these subsystems separately, we can model each and every system. And after getting the mathematical model, we can again recombine this and to get the final output. This is mentioned in this pair. So dynamic mechanical elements are made of masses or inertia, which have attached springs and dampers. If we consider the mechanical elements, so dynamics of mechanical elements, we can model with the help of masses, inertia, etc., etc. So that you've seen, you will be familiar with all the things. Now look at table 1 and 2, where various elements in their governing equations are summarized. Come to the mechanical models. First one, the mass. We can model this mass by this governing equation, F equals to m dV by dt. What is F, what is m, and what is dV by dt? I think it is very simple. What is required here? Just see this table and please remember how the mass can be represented with this governing equation, where F is force, m is mass, dV by dt is change in the velocity. I think so. Hai na? F equals to m, dV by dt is the change in velocity, means acceleration. F equals to ma. Force equals to mass into acceleration. So in this way, we can represent this. Similarly, for thermal means depending on the change in temperature, what happens to a capacitor, what happens to a resistor. Similarly, the electrical elements like capacitor, inductor, resistors also the electrical elements. So with these elements, if suppose some sensor is represented by a combination of mechanical, thermal, electrical elements. So we will divide this into three parts. First, the mechanical, let's say mass. Second, thermal, let's say capacitor. Third, electrical, let's say inductor, resistor, capacitor, everything, or any one of them. So then we will look at the governing equation, and after getting the governing equation, we will combine this, and then we will represent the complete mathematical model of the sensor, and then we will say this is the complete model, this is input, this is the output. For example, if we consider monoaxial accelerometer as it is shown in this, and this is nothing but thus example of, you can say, we can relate it with the piezoelectricity. Some force is applied here. Because of that, something happens. Deformation in shape will be there, and then it generates electrical field. So we can just compare with the piezoelectric crystal. As mentioned here, the mechanism of conversion may be, for instance, piezoelectric. Okay, so if this is the case, what happens? Some force is applied. What will be the actual thing that will happen inside the crystal? And that can be represented by a spring connected with a mass, then a damping element. And for this, we can write a mathematical expression with the help of Newton's second law. mf equals to minus kx minus b. That I think you know. Kx and bx, the energy stored in the mass spring. So to compensate that, two masses must be equal, where F is the acceleration of mass related to the F is the force. F equals to d square x by dt square minus d square by dt square. This is the, please don't worry about the mathematical expression. Just I took to explain one mechanical dynamic of mechanical elements. So after putting this value in this equation, these two forces we equalized, and then we will get a quadratic type of equation. Correct? So this above equation is of a second order, which means that accelerometer output signal may have the oscillating shape. By selecting an appropriate damping coefficient B, the output signal may be brought to a critical damped state. Damping means, suppose there is some fluctuation in the output, means oscillating nature. So to keep these oscillations minimum, some force is required. So by selecting that damping force B here, we can restrict the oscillations to get the stable output. So this is just one example. Similarly, we may take examples from electrical elements, we may take thermal elements, and depending on the elements used in a sensor device, we can mathematically model it. But here, for you, we will not go in the mathematics of that. So what we must know? We must know these three things, means the mechanical analogy, thermal and electrical analogy. If I say there is one spring, mass, a mass M is attached with this, some force is applied, this type of the governing equation or the mathematical model we will have for this system. So with the help of these components, means the mass, spring and damper, you can model it. Similarly, for capacitance, if it is thermal system, then definitely some change in capacitance will change the capacity, some resistance will also be there. So how we can represent a thermal resistor, how we can represent a thermal capacitor with respect to change in temperature. So the capacity of the capacitor, okay, it depends on the variation in the change in ambient temperature. So how it can be modeled? So these equations we must know how they can be represented. So only requirement is this one. So if we have a sensor system, it may have different elements. Based on the elements, we can subdivide the sensor system into number of parts. One element, second, third, fourth, etc. Then we can write a governing equation for different elements, and then we can combine these to get the mathematical model of complete system.